Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and today I'm talking with Peter Delos, Principal Engineer in the Advanced Data Converter Group at Analog Devices. Welcome, Peter.
Yeah, thanks. Thanks for having me, Pat. Happy to be here.
So, in this conversation, I thought we would explore the evolving landscape of direct RF sampling data converters and kind of focus on the impact on phased array systems. So, can you tell us, Analog Devices is historically known as a data converter supplier. What are some of the recent developments and where do you see data converter world transitioning to?
Okay, yeah, thanks, Pat. Great introduction. So maybe we should start with where the world is going or where we see the world going, and we'll talk about what we're doing. So there are many pushes, and the applications and the technology are sort of coming together to enable direct sampling converters and pushing the sample rates higher and higher. Some of the motivations are swap integration in particularly phased arrays, other small form factor radios, and enabling what used to be much larger systems in much smaller footprints or many channels needed for phased arrays. So that's sort of at the larger drivers. Now, what are we doing? So we're known as for the components, different piece parts, particularly the data converters are a strong legacy for us. I'm actually in the data converter groups right now, working on some of our next things. But the most recent things that have come out are the combination, I would say the combination of the converters, the attach RFICs around it, the PLLs, RF parts, a whole suite of embedded DSP to deal with operating at the higher sample rates. And those things together provide like a full RF sampling solution. And if you think in those terms, there's basically RF comes in, pre-processed data goes out to FPGAs or ASICs, and that's really the path that we're on at the moment.
And that's interesting. Maybe you can elaborate with an example, but I think there's always kind of a trade-off between, kind of power consumption and how you configure the system. I know everybody likes to be all digital, but at some point, there's some trade-offs you have to make.
Right, right. So we can talk through some of our recent releases. The AD9084 is an example, and you can look on our websites and see that. So that's direct RF sampling, input bandwidth up to 18 gig, A to D rates, 20 gigasample per second, DAC rates, 28 gigasample per second. There's a suite of parts that can go with it, PLLs, attached parts. We have reference designs of multiples of these on a board. And we have a whole suite of embedded DSP to basically help with your question of how to deal with this data rate. Now, this isn't the only type of option. So in this type of option, the power savings actually, there's a lot that's saved in past designs through the LO, the mixing chain. There's a lot of power that goes into that. Now, there are reasons people may want to stay with heterodyne type architectures. We enable that. We encourage it. We provide all the parts to do that. But for the smallest form factors and actually the lowest power, the direct sampling up to a point is actually very efficient. And so those are the things that we're doing. And it's the combination of miniaturizing, removing some of the past functions, and then also putting the embedded DSP in ASIC form inside the converters to save power that would otherwise be utilized in FPGAs. And then the FPGAs can move on to higher levels of processing and so on.
Yeah, ADI has a lot of choices in their portfolio, but I've always wondered about the data converter clocking at these rates. How is that handled?
Yeah, that's a great question. So as we moved up to these rates, actually we thought very specifically on this. So as we take the 9084, Apollo's our trademark name for that. The inputs are 20 gigasample per second, and so you can provide your own clock into that, and we support that, and we have many customers doing that, particularly instrumentation or high-end systems. But it's a challenge, and there's a lot of effort needed for that. So we made basically co-designed with it one of our PLL chips, the ADF 4382. You can look that up. It's released and online. And that on our eval boards, you'll see that sits right next to the data converters, and a much lower frequency reference can come into that. And that enables this whole direct sampling to come together with sort of minimalist effort from the user. And you can take our reference designs and just copy them into your layouts and build up around it. And so that's how we've handled that particular piece of the puzzle.
And what impact does the clock performance have in the overall system performance?
Yeah, yeah. Okay. So another good question. So for the RF engineers out there, you can think of the clocks to the converters similar to how you used to handle the first LOs in past systems. And so let's take, any type of heterodyne, and it wasn't too long ago when the converters were say in the 100 megahertz, there might be a dual down conversion stage to get to the before sampling. And the first LO, which is sort of a radar term for the highest frequency LO that drives the mixers, that's at the highest frequency, and that set the system performance for many types of parameters, particularly phase noise and some of the other things. Well, in direct sampling, it's going to be the same impact. And so you can think of the clocks to the converters as this similar to the LOs, and they need the same care in your design and your distribution. And you want to keep that separated from the all the digital and on in its own domain coming into the data converters, regardless of which converters you use. And so if you think of the clocking similar to how like LO distribution was handled in the past, then it becomes much more clear how to optimize your system for that.
And we'll come back to the overall noise performance, but you mentioned embedded DSP. Why wouldn't someone just buy an FPGA and process the ADC data directly?
Yeah, yeah, that's another good question. And two answers. First of all, people can, we support it. If you want the full rate A to D data out, you can get it, and we have modes for that. But in many cases, it's just not the most efficient way to handle things. And if your processing bandwidths are a fraction of your sample rates, then we provide a whole set of embedded DSP. It's in ASIC form. There's power associated with using it, but it's much more efficient than soft programming your own fabric, and it's much faster. There's an API language you program into the part. It's all built in and ready for you. And that includes digital down converters, there's filters, there's FIR filters, there's a built-in FFT, more of a spectral monitor, there's some loopback paths, and these things are very much more efficient in ASIC form. And as we look into the future, that's going to grow. And so we've offered that now in the 9084. That type of work is going to grow into the future, and then it basically is an augmentation to the FPGA work. So all your digital designers, it doesn't change what you're doing. It's just an assist, and then you can focus in the FPGAs on whatever you're really trying to do, and use what's built in and programmable, and put your special sauce, whatever you're trying to do, into your own code, and that's the way to really optimize the system.
And so, coming back to performance, as phased arrays migrate to digital beamforming, there are many converters in that system, and there's much discussion around the array gain and dynamic range improvements as channels combine. What do you describe to help our audience understand this area?
Yeah, that's a great question, and it's an area for people newer to phased arrays. You hear about this array gain, and it's a little bit confusing initially. What is it? Is it real? How do we make this work? We have several articles out on this. We have some more coming with some of the Quad Apollo work that we're doing. And the general premise, if you start think in terms of even just a power combiner, when you're combining two signals, if the signals or main signals are in phase, you'll get a 20 log n improvement, or basically voltage noise will be 20 log n, power will be 10 log n. And then if the noise is uncorrelated, you will see essentially when you combine channels, you'll get a 10 log n improvement. So the first step is to visualize this with two channels, and then you can visualize how to extend it outward to the whole system. The tricky part is tracking what's correlated and what's uncorrelated. And so correlated terms are generally things that are shared. If there's shared LOs, shared clocks among channels, those whatever noise component of the final noise, that'll be correlated. So you can map this out thinking from a clock and an LO perspective, and then actually become very accurate in some of the predictions. We have some app notes out on that, and I can send links at the end. Spurs are a little more tricky to do. There, you can think of them more as signals, but the main thing is to figure out methods to ensure, regardless of where they're coming from, you separate them into terms, whether they're mixers, spurs, A to D spurs, DAC spurs, and come up with ways to make sure they're not the same across channels. And that could be phase, frequency. And if you do those steps, you can achieve array gain. And then if you track what's correlated and uncorrelated, you can actually predict quite accurately where you can end up in the end. And it takes a little bit of work at the beginning, some new ways of thinking about things, but breaking it out that way can be very fruitful and actually economical to not push, power and unnecessary performance where you don't need it.
And you've developed some demonstration platforms in this area, right?
Yeah, yeah. So we have two that are out that we would recommend looking at. So the quad MxFEs came out, I think through COVID, we've released that and have most of the app notes that are currently published are with that. There's Quad Apollo, which is 49084, so 16T, 16R. Both of these are 16T, 16R platforms. There's a whole suite of software that comes with it. There's MATLAB control, so you can quickly get it up and running in your lab. You can look at some of these things, and we've used those as a baseline for to publish some of these types of principles. And so those are we'd recommend if you're looking into this multi-channel world and trying to get a head start on with reference designs, we've provided those for that reason.
Yeah, you've provided a ton of information, so where can people find out more details?
Yeah, so I'll send you some links after we're done, Pat. A couple app notes, reference, links to some of our recent parts, and encourage anybody just to get back to us directly, and we can get the right people to you on any other additional topics.
Great. I'll put that in the description. So thanks a lot, Peter, for talking with me today about data converters and their impact on phased arrays, because it's quite interesting the way you configure systems. To our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.